All right, the last little topic here I want to talk about in the 8.3, the trig substitution thing. Oh, excuse me. I should have taken a drink before I started the video. Is anytime we have tangents and secants. So tangent to some power, secant to some power. Integrals of this form. So these are a lot more difficult than the cosines and sines. There's not just easy cases that we could put for this. Look at this. The Stanmore index is what they thought I wrote right there. So for this, we're going to be using a couple different techniques. The first thing is that we can still use the Pythagorean identity, just the Pythagorean identity for tangents and secants. So just rewriting it around a little bit. You could have tangent squared is secant squared minus 1, or just solving that for secant squared, we get secant squared is tangent squared plus 1. So sometimes this will help you with solving the integral. Another technique that, another thing that you can do is u substitution, of course. Remember that if you let u be tangent, the u would be secant squared. Or if you let u be secant, du would be secant tangent. So anytime you have like a rogue secant squared or a rogue secant tangent laying around, sometimes doing the u substitution this way will substitute that out to be du's. Another thing that you can do is integration by integration by parts. So this is used whenever you reduce higher powers. All right, let's look at just two examples here. So the first example will be the integral of tangent to the fourth. Now I know that's a higher power and you could probably do some integration by parts to get rid of that, but because tangent squared breaks down so nicely into secant squareds, we're going to do that instead. So we're going to think about this as tangent squared times tangent squared. And then one of these tangent squareds we're going to substitute using the secant squared minus 1. If I then distribute the tangent squared into this parentheses, let's kind of break here and let's talk about it. Okay, so first off, this first term. This, we can do a u substitution. Because if I let u be just tangent, then du would be secant squared, which would make that go away. And I would just have the antiderivative of u squared. This one's going to be a little bit more difficult. That we cannot do yet. However, I can do another substitution replacing that with secant squared minus 1. So let's do that. For now, I'm just going to leave this one alone. Tangent squared times secant squared. But then this, I'm going to substitute with secant squared minus 1. That minus sign is going to have to distribute in, so let's go ahead and do that. And now everything here we can find the antiderivative of. The secant squared has antiderivative of tangent. 1, of course, has antiderivative of just x. We have to do the u substitution for this first one, so we're going to let u be tangent, which means that du is secant squared. So this first integral is really the integral of u squared du, which has antiderivative of 1/2 u squared, but then we're going to plug back in the tangent. Okay, so starting back up here, the whole thing is going to be 1/2 tangent squared, so that's just from here, minus secant squared has antiderivative of tangent, plus 1 has antiderivative of x. This, if you were to take the derivative of it, would get you to tangent to the fourth. I know it doesn't look like it, but I promise you it does. Okay, great. So let's do one more example. Let's look at the integral of this one, we're going to do integration by parts, and I think it's brilliant. It's really cool how it works. So remember with integration by parts, we need to set up a u and a dv. The u is just going to be a single secant, which means the dv is everything left over. We're going to let that to be secant squared because we can find the antiderivative of secant squared. That's going to be tangent. So du is the derivative of secant, which is secant tangent. Don't forget the dx. V is the antiderivative of dv. The antiderivative of secant squared is just a single tangent. Remember that the integration by parts is uv minus the integral of v du. So u times v is going to be secant tangent minus the integral of v du. I'll write that as secant tangent squared. Okay, so now we just have to find the antiderivative of this. All right, for this one, we're going to do the same thing. We're going to change that tangent squared into secant squared minus 1. Distributing the secant. Okay, here's the fun part, right? So again, we end up with a secant cubed integral on both the right-hand side and the left-hand side. What I'm going to do is I'm going to add that back over to the left-hand side. We're going to end up with a 2 integral cubed x dx on the left. We still have the secant x tangent x on the right. And we have the double negatives cancel, so plus the integral of just secant x dx. This one is hard to do by yourself, but remember we have that table of integrals that's on Moodle that I sent out already, and the integral of secant is on that table. So we still have the 2 integrals cubed. We still have the secant x tangent x. If you need to pause the video and go find that table of integrals, do that. But the integral of secant x is the natural log of the absolute value of secant plus tangent. And we can throw the plus c in here in a minute. Last little step will be dividing by that too. So the integral of secant cubed is 1/2 secant x tangent x plus 1/2 natural log secant plus tangent plus c. All right, so a lot of techniques there. We had the integration by parts where we had to wrap it back around to the front. We had the table of integrals. We were using Pythagorean theorem with tangents and secants. So like I said, with secants and tangents, they can be difficult, but are 2 techniques. From this last example, we just did the Pythagorean identity and then a u substitution. This example, integration by parts. So try both of them. You're just going to have to play around with it. There's not really nice cases. It's just using the identities, using integration by parts, using u substitutions to finally get to the antiderivative here. Okay.